Okay, welcome to the new video. We've been discussing about finite groups. In that context, let's take next example. Okay, so what we have is let G be a abelian group. G be a abelian group. Okay, and and let H and K be two subgroups of G. Right? Then H dot K, right? This multiplication is defined as h into k. This hk, the product hk, it's defined as h into k, where h is coming from h and k is coming from k, right? So how does this product? You take an element. In every element in hk would be represented as a element in h multiplied by an element in k. Okay, is a is a subgroup is a subgroup of G. Okay. Now you need to be careful about the property. It's given that G is abelian, right? G is abelian, so you need to be careful, right? If this um, information is not there, that means G is any group. Then HK need not be a subgroup. Be careful. This is not true. Okay, this is true only when G is abelian, or there's some property of on H and K, okay, which you would get as we proceed further. So this theorem you need to be very careful. It's rather, this problem is you need to be very much careful, because if H and K, I mean, sorry, if G is not abelian, HK is not a subgroup. Okay, you can take an example rather. When G is not abelian, you take two subgroup and you look at you look at all the products. Um, you'll find that uh, it's not a subgroup. Okay, we can think about a problem, maybe in the chapters coming, wherein we'll be encountering with non-abelian groups, more non-abelian groups. So far, we only have seen only dihedral group, right? Instead of matrices, of course. Anyway, let's proceed with the solution. Solution is pretty easy, because it's all we have to use, as I said in my previous videos, that all we got to do is use, whenever we need to show something is a subgroup, all we got to do is use one subgroup test, right? Or maybe you can also use two subgroup test. Okay, it's up to the individual what he wants to do. All right, then let's look at let's use one subgroup test. Somebody can do, I can leave that an exercise. Use uh, two step subgroup test step subgroup test to prove the same. Okay, I'm just going to use one subgroup test. Somebody can just go ahead and try proving using two subgroup tests. It's just left to the individual, okay, whether he wants to do it or not. I'm using one subgroup test. So what I'm gonna do is I'm taking two elements. Let say A comma B belongs to HK, right? My claim is A B inverse is in HK, right? That's what I'm claiming, right? Right. So right. So let's go further. Okay. All right. So what I'm claiming is AB inverse belongs to HK. Okay. Now so uh, since since A comma B belongs to HK. This implies there exists K1, let's start with H1 for that matter. There exists H1, H2, right, in H, and K1, K2 in K, such that um, H1 K1, A is H1 K1, and B is nothing but H2 K2. Uh, well, let's look at what happens to AB inverse. Therefore, AB inverse would be nothing but H1 K1, right, multiplied by H2 K2 inverse. Isn't it? This is equal to H1 K1, right? There's a dot in between somewhere. Yeah, forget about that. Do that thing. Since G is given to be abelian, H2 K2 inverse can be directly written. This is nothing but H2 inverse K2 inverse. We have already seen the property that G is abelian if and only if AB inverse is A inverse B. So now since G is abelian, these all elements are in H and K. Of course, H and K as subgroups. So what will happen is I use the property that G is abelian and write this as H1 multiplied by K1, right? Beg your pardon. I can just take H2 inverse here. H2 inverse, right? And this would be multiplied by K1 into K2 inverse, right? Now, since H is a group, right? Let's just do that. Okay. Right. Error. Okay. All right. Since H is a group, what happen is since let me write this. Since uh, H is a subgroup of G, this implies that H1 H2 inverse belongs to um, H, because it would be closed under multiplication, right? Two elements, if you multiply them, it's inside, right? And similarly, also since K is a subgroup of G, this would imply that a K1 into K2 inverse is in K, right? So let, what I'm doing is let H, capital H, be H1, um, H1, uh, H2 inverse, and let me, or I don't even have to do that, but anyway, we would do that, and let K be equal to K1, K2 inverse, right? Right, that's fine, right? This implies what? AB inverse is equal to H times K, which would belongs to, and since A and B were arbitrary elements, right? In HK, this implies that AB inverse is in HK, right? For all A comma B in HK, implies that HK is a subgroup of, clear? All right. As I said, let's 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 I mean um, let's look at next problem. Uh, you, uh, yeah, the next problem. Okay. Uh, example. Example here. Example. Let G equals R star with multiplication. Let it be the real general multiplication of real numbers. Let H be equals to set of all x in R, right? Such that x is equal to 1 or x is irrational, right? And k be equal to set of all x in R such that x is greater than or equal to 1. This is fine. Okay. So I'm taking H to be set of all elements. If either X has to be one, that is a multiplicative identity, or it has to be irrational, and K is equal to set of all elements which are bigger than or equal to one. Okay, then let's check whether H is a subgroup. Okay, check if H and K are subgroups of G. Okay. Solution is straightforward. You can directly see that H is not a subgroup of G, as what happens is um, it's not closed with respect to taking products, first of all, because if I look at root 2 is in H because it's irrational, right? And also, okay, I can directly root 2 is in H, but root 2, you know, multiplied to itself is 2, which does not belong to H, right? So it's not closed with respect to the multiplication of R. So therefore H is not okay. Similarly, um, K is not a subgroup. Okay. Similarly, K is not a subgroup. The reason is again, um, I mean, I won't tell you this. Please find out why is not a subgroup of G. Why? Why on earth would that be the case? That K is not a subgroup. Okay, you can verify why it's not a subgroup. I'll leave it. Pretty straightforward. Um, I wouldn't tell you that. Or yeah, I wouldn't tell you that. Of course not. Sorry, but it's pretty straightforward. You can just go and check it out. It's not a thing. Yeah. So let's go and just do more things. Uh, okay, so let's look at this theorem. Okay, it deals with how do I check whether a finite set is a subgroup. Okay, so theorem. Let H be a non-empty finite subset subset of a group G. Okay, suppose if H is closed under suppose H is closed under the operation of G, then H is a okay. So if you have a finite set in a group G, then it's a subgroup. If it's closed, sorry, under the operation of G, then it's a subgroup. Okay. So all you got to check is whether it's closed with respect to the operation. So let's try to prove this. Okay. Um, what we would do is we would use two subgroup tests because it's already given that it's closed. So all we have to show that it's closed with respect to inverse, right? So let's do this. Since H is closed with respect to the operation of G, it suffices to show that A inverse belongs to H for every A in H. Right? That's all we got to show. Okay. All right. So let's look at this one. So let A belongs to H. Okay. Suppose A is equal to identity. Okay. That means H has only none. No, suppose A is equal to identity. This implies A inverse is also equal to identity, and that is in H, and we are done. And that's it. So if H has only one, of course, it's not necessary. If A is whatever element we are picking, if it's identity, we don't have to prove any further. So let A not equal to identity. I mean to say uh, if uh, A is equal to identity, there's nothing to prove that A inverse has to be in H. Okay, we got to prove it for that's trivial. That's what I mean, right? If A is equal to identity, its inverse will always be there. So there's nothing to prove in this. Okay, so it's pretty trivial. Okay, we are done means there's nothing to prove. Okay, that's pretty trivial. So let A inverse, let's prove that A inverse is in H for some other element apart from identity. Okay. All right. So I've already considered A in H. So what we do is uh, let A be not identity. So consider a sequence a, a squared, a cube, a power 4, so on in H. So let me take a sequence, right? A square, a cube, so on up till powers of a rather in H. Since since uh, H is finite, right? Not all elements of the above sequence are distinct, right? This sequence cannot go on in H, right? Because H itself is finite. So this implies that there exists I comma j, right, in Z, right? Uh, well, you can in N also, it doesn't really matter. Such that a power I, there will be two integers, right? Would give you or rather, uh, yeah, doesn't really matter. I would get e raised to I is same as a raised to j, isn't it? These two elements, at least two. I mean, at least you know, I would have at least two elements whose power is same because h is not. I mean, it's finite. Okay, so this implies that let's suppose from here, what I can assume without loss of generality is I is bigger than j. Of course, you can uh, assume otherwise, but that's fine. Okay, so since A is not equal to identity, right? This implies whatever, if since A is not equal to identity, this implies that I minus J. I'm just assuming, if you want, I'm assuming that I is bigger than J. Of course, you can also assume that J is bigger than I. There's no problem in that. I minus J is strictly bigger than 1. Okay. since A is not equal to identity, it cannot be 1. I minus j cannot be 1. Because from here, what would I get is A raised to I minus j would be equals to identity. If I multiply um, A raised to minus j on both sides, what would I get rather is identity. And since A is not equal to identity, this I minus j has to be bigger than 1. Okay. So therefore A, right, let's look at this one. A into what happens to this? A raised to I minus j minus 1. Okay. What would happen to this? This would be equal to A dot, right? A raised to I minus j minus 1, right? This would be nothing but A into A raised to minus 1 into A raised to I minus j. This is nothing but identity, so this would be A inverse, which is identity. Similarly, A raised to I minus j minus 1 would be, sorry, into A, of course, into A minus j minus 1 into A will also fetch your identity, right? This implies that A inverse is nothing but A raised to I minus j minus. It's clear? This is the inverse, right? And its inverse is also some power, right, of A. This implies that A inverse belongs to each, right? Because since this is bigger than 1, this would imply that from here, since this is uh, as yeah, that you don't have to say, but just make sure that you understand this. This is a positive power of A, because I minus j is bigger than 1. That means it can be 2, 3. So whenever I say I minus j minus 1, that would be bigger than or equal to 1. So this would be some positive power of A, and I'm taking all this in H. So this is also an element. So A inverse will be somewhere in between this, right? Its inverse will also be somewhere in between this. That's the idea of the proof. Okay. So what does it prove is A inverse is in H. Therefore, by two subgroup test, H dot E. And that was pretty straightforward, right? All right. So let's look at certain notation I've already done when I was doing this examples of a group generated by a single element. So let's look at this one. Let's fix our notation. I mean, I've already done that, but let's make it official here. So let G dot, because I'm gonna prove this uh, result. Let G be a group. Okay. Let A be in G, then we know that this is set of all A raised to N is in Z. Um, well, yeah, that's fine. And this when I'm talking about additive groups, this would be N dot A. Just a moment, I think I've done a mistake somewhere in the above proof, because I was talking about the positive powers, right? I would have to make sure that because I was talking about the positive powers, of course, but that doesn't make any difference. But let's be very precise in our proofs. Okay, so let me take this to the end. Doesn't really change any effect, but at this I've taken positive powers, so let's be precise in our. I hope that doesn't change anything from your side. So we have already seen that this is a set, and it forms a group. Okay, right? We'll show that this is a subgroup first of all. Okay, so let's fix this notation that A is nothing but this when we are talking about multiplicative group. This is when I talk about additive group. So this is true when I say it's additive group. I think I've already seen this. This is called as group generated by, it's called as group generated by A, and it's a subgroup of G for every. So let's prove that result. Theorem. Okay. Let G dot be a group, right? Then A, right, which is nothing but A raised to n. I'm using for multiplication. I mean, I'm just using this. It's the meaning is clear whenever the operation is specified. Okay, this is general. N in Z is a subgroup of G for every A in G. Okay, so it doesn't matter what you take. We have already seen that it's a subgroup. Okay, so the proof is pretty straightforward. All I got to do is use one subgroup test. Okay, so um, let's look at this one. Right. So what we would do is first of all prove that this set is non-empty. So since A belongs to A, right? Isn't it? A, because any set which is generated by A must have A inside that. So this implies that this is non-empty, right? So let x comma y belongs to the set generated by A, okay, right? So what would happen is therefore uh, see, I've already given, okay, there's a problem which I'll just say that a little bit later. So this implies x would be equal to some a raised to n, right? And y would be equal to some a raised to n, right? For some m comma n in z, right? Therefore, what will happen to x, y inverse, x dot y inverse is this will be a raised to n into a raised to m inverse, but we have already seen that this is nothing but a raised to n into a raised to minus m, I can say this. So this is equal to a raised to n minus m, right, which is belongs. So n minus m is some integer. So x y inverse is some a raised to integer, right? Therefore, x y inverse belongs to a for every x comma y a, and the proof. And one thing I want to remind you is what we have done. I'm sorry. One thing I want to remind y'all is if I just have named this as group generated by A. Okay, I had not proved it, but I just named it before even proving that this is group generated by. But I mean, it's I hope it's all right. Okay, because so here I've already proved that it's group generated by, so it's no problem in that. You know, just thought of letting you know. So let's look at some remarks. Okay, based on the above theorem. Okay, so first one is A is a subgroup of G and it is called as cyclic. subgroup of G generated by A, or you can also similarly call group generated by. Second, if AI AJ belongs to A, then A raised to I into A raised to J is nothing but A raised to I plus J, right? Which is same as A raised to J plus I, right? Which is A raised to J into A raised to. So what does this prove is every cyclic group is converse is not true. We would see this in the next chapter. What are cyclic groups? Okay, but for the time being, it's enough that we understand this. Well, we would learn about cyclic groups in detail in next chapter, but for the time being, let's understand certain examples. We will take more examples as we go along in the third chapter. Okay, so example Z with respect to addition, okay, is a cyclic group as Z is generated by 1, right? Sorry, I made a mistake. Do this carelessness all the time. So, uh, because Z is generated by 1, right? 1 generates Z, and minus 1 also generates because it's if you keep on adding minus 1 is the inverse of 1 first of all. So if an element generates its inverse, will have the same order first of all. And how does this generates? Because how can I write 1 can be written as set of all uh, n times a, that means n times 1 where n belongs to Z, right? But what is this? This is nothing but n times 1 is n, right? N belongs to Z. So what is this? This is nothing but Z. So that's fine. Okay, and similarly you can do that with minus 1, because if one generates, if A generates its inverse, A inverse will also generate the same group as we have seen. Okay, uh, all right, just one example. Let's look another example. Let's take u10 with multiplication modulo 10. What is u10 for that matter? U10 is 1 3 7 9, right? And we have already seen that um, uh, if I look at 3, powers of 3, what I get is 3 raised to 0 is 1, then 3, 3 square is 9, right? And 3 raised to 4 is uh, 3 raised to 4 is 27, that's 7, and 3, sorry, 3 raised to 3 is 27, 3 raised to 4 is 81, which is 1, right? So what I get rather here is U10, complete U10. Okay, it generates the group, right? Right. So it's 7 here, 7 here, 7 here. So it's entire U10. Okay. What about the inverse of 3? It would be 7. So 7 would also generate the same group, right? Which is U10, right? So that's therefore U10 is cyclic. Therefore U10 is a cyclic group. Okay. U8, not necessary. U8 is not a cyclic group. An example of not a cyclic group I can take. Okay. Of course, R is not cyclic because there's no element which would generate R. Uh, so uh, yeah. So finite group. Let's take example 3. U8 with multiplication modulo 8 is not cyclic as what is U8 first of all? Let's look at this. This is 1, 3, 5, 7, and every element has order 2, because if I look at one will I mean identity would never generates, so this is one. Remember, one is not a identity as in when you take addition. Okay. Anyway, multiplication, it doesn't even form a group, so it's immaterial. What is 3? 3 is nothing but 1 3, because the moment you take 3 square, you get 9, which is 1, right? Then you take 5, this 1 and 5. See, every element has order 2, right? You can check that, right? And as a group is cyclic if you can have a element. You need to have an element whose order is equal to order of G. So that's the idea. Okay. So this